Good morning, students. As we discussed in the last video, we designed one lumped matching circuit. So we'll go for another design of pi type. In the last video, we have discussed for L type. Now I'll show how to design a pi type matching network. So you first create a new schematic window and name it as pi type matching, or any name you can give. Better use the same name of the circuit so that it will be clear when we verify it. Okay, so now window is open, the schematic window is open. So what is the next step we will be doing here is we'll go for opening this Smith chart utility tool, and with this Smith chart utility tool we'll be creating the pi type matching network. So now I'll go to tools. Under tools, you have Smith chart utility tool. As soon as you open the Smith chart utility tool, you can see, as I told already, there is one palette window where all the components which is used for matching is discussed here. And there is one more two terms which we should feed initially when we start our design: frequency and characteristic impedance Z0. Then we have a Smith chart window, a network response window, network schematic window, and we have lot of things given here. What is a gamma, VSWR, Z and Y values for the Z0 value, whatever we are feeding. Okay, so now I'll even select this Y type circles also, admittance circles. Now for what is the design we are going to do right now is we are going to design two impedance matching network, like pi type matching network, which is having a ZL value I'll mention, and I'm designing this matching for 2.4 gigahertz frequency. So I'll write first 2.4 gigahertz, and ZL value what I'm going to give now is I'm going to give the ZL as 10 minus j again 10. Okay, so this is my ZL, and now what will be my ZS, you can check. I'm going to choose the ZS as the ZS what I'm going to match now is 20 plus j 40, but when I enter here it should be 20 minus j 40. Okay, because we already discussed in the last video, conjugate matching should be applied, so I'm applying conjugate matching. So where is my ZL point? It is somewhere here. When I click on ZL I can see my ZL point. When I click on ZS I can see my ZS point. So now what is my stop frequency? My center frequency only is 2.4, so I will choose the stop frequency as 5 so that my response will come exactly in the middle of this graph. Okay, so now we'll start a pi type matching. So if I want to start, I'll move from ZL. So what are the possible ways I can move is I can go up in the resistance circle. Okay, and then to some extent I can go up, then come down, have a break again here, then again I can have a movement over down in the Y circle. Or what are the other ways? I can start down. Okay, I can just come till this and directly reach this, but only two elements will be used if I go for the first solution. I'll just tell you what are the different solutions I can use. Suppose if I take a capacitor, okay, if I'm taking a series capacitor. When I take a series capacitor will always move down, okay, along the resistance circle. So till this point I'll come and stop. After that I will move up in the conductance circle to reach this point. To move up in the conductance circle, I'll take a, if I take this, it's going up. I'll go for, see this one. So now from this point I'm moving up. To move up in the conductance circle, I'll take the shunt inductor. So I'll just go up and click it. So this is one type of matching. This is a solution 1. Okay, this one what I have done is a solution 1, and you see the response that is exactly in the middle, coming more deep at 2.5 gigahertz. But what is the thing I'm going to do now is I want to do a pi type matching. So I will select the particular component, delete this component, because I want to construct now with 3 element. Okay, so now I'll start from ZL. So what is the second solution I can do is, I can go up in the resistance circle. So I'll take a series inductor, come up to till where? Till this point I can come up. Okay. Then come down in the conductance circle. So coming down in the conductance circle, I can select, it's going up capacitance. So now I'll select shunt capacitance. So it's coming down here. Till this point I'll stop. Again I have to have one more pi type. So I can come down like this, but if I come down again I should select one. I should select what? Again a capacitor, but it will come here, but it will form like this. But I want a pi type. So what I will do is I'll select the particular component, delete it. So I want to have one thing which is starting from one shunt element. So I'll delete this particular component. I'll start from ZL now. Okay, this also I'll delete. So now I'll start from ZL. I will go for one. It is following the, see this path, it is following the shunt, it's going up in the conductance circle. I'll click here. Okay, now I'll go and select one capacitance. I'll come down till this point, then again I'll select one inductor. So this inductor is going up. So this, so can you see I have formed one pi type matching circuit. So I am moving from conductance circle up to the this point resistance circle. From there again I'm coming down in the resistance circle. From there again I'm moving in the conductance circle. So this is one kind of configuration. So you check what are the values we had found out. So we have first found out the value as 661.2 picohenry. Then we have got the capacitor value is what? Capacitor value is 1.638 picofarads. And we have got another one as 6.83 nanohenry. So totally I have got three components for the frequency of 2.4 gigahertz and the characteristic impedance is 50 ohm. So now I will keep this as such. I'll come back to the schematic window. So here what I'll do, I'll first form one inductor, a basic inductor I'll take. I need two inductors. So I place two inductors. This one I'll rotate. Even this I will rotate, and I'll keep one capacitor in the middle. So this is my matching circuit what I have, pi type matching what I have constructed. So using the line, using this wire I have connected all that. Then I'll go for connecting one terminating resistor. So where is the terminating resistor? Go to simulator S parameter. Under simulation S parameter, you have simulation S parameter controller, that also you put. Then you have the terminating resistor. Put two terminating resistor in both the sides whose impedance now I'll change. Okay, according to my design what I have taken, I'll change the impedances. So now all this one I'll connect it and I'll ground the other end, because that circuit will not be closed if you didn't connect it. So I'll connect all these points. Okay, then I'll come back here, I'll ground it. Okay, so now what is the impedances I have used here is, my input impedance I have given as output impedance is 10 minus j star, again 10, whereas input impedance I have taken z star there, but here I have to give the actual value. It is 20, it is 20 plus j star, again it is 40. There I have given 20 minus j star 40. Here I am given 20 plus j star 40. And what is the values of the inductances? So go back to the window here and check what all the inductance values you got. So the first inductor from the ZL side, if you see, it is 661.2 picohenry. So I'll come here, I'll write here as 661.2, it is pico. And here what is this inductance value? That inductance value is 6.83 nanohenry, and this capacitance value, if you see, it is 1.638 picofarads. Okay, so I have fed the same values whatever I have calculated from the Smith chart utility tool. Okay, so now I'll go back to the schematic window. Here I'll start the frequency range. I'll start my simulation response from 500 megahertz to 5 gigahertz is enough for me, and in the step of 0.5 I'll give, or 0.1 I'll give. Okay, so that I can see the response exactly. Is it clear? So this is the till forming the matching circuit with this to verify whether the matching is properly done with this. So I can bring it everything in the middle. So you can make your schematic looking better by adjusting this. Then now I'll save this and then go to simulate option, simulate. Simulation is running. Any errors, if it is coming, this will be observed in the screen. If there is no error, then nothing is there. We'll get another window. This is a data display window where I'll go for plotting the graph. I'll take the rectangular graph. I'll plot for S11. Let it be, when you go for clicking this add button, you will get this small window where you will select it as DB. Give OK. So you got one response. Now you select S22 also. Okay, let it be in dB, and you select one more, that is S21 is a gain or insertion loss. Okay, so now if you see at 2.4 gigahertz, go and keep the marker, insert the marker here and bring this square box inside. At 2.4 gigahertz I'm getting very good response of minus 35. One more marker I'll place in S22 also, bring that also inside, same 2.4, you're getting a very good response. So when I come to this at 2.4, what is my insertion loss? So I'll move this at 2.5, it is showing. At 2.4 I'm getting 0, close to 0. So my responses are very accurate. I can go and double click on this the graph red color one what is formed, and you can increase the thickness to make it looking better. Okay, I can just click on that. You can increase the thickness little bit and you can just have your very nice plot. You can change even the colors also, the options are there. You can even go and click on the nature of the graph. Instead of keeping it what color you want, you can keep, and you can change in short dot dot or short dots, short dash or long dash. Okay, so this is the output response you get for a pi type matching network. Okay, so we'll go back to the schematic and we have to see our circuit is working fine with this. So we get a very good response of minus 35 dBm. So if you see here, you got a response of minus 35 dBm return losses at input as well as output, and you are getting a 0 dB insertion loss. So it means the matching is done perfectly with pi type matching. So now I'll continue with the same video how we can go for constructing a stub matching. So for that, I'll save this window. I'll open a new schematic. Okay, I'll go back to the, I can go back to my uh, workspace window. There I'll create one new schematic again with stub matching. Okay, stub matching I'll create. Stub matching is next example what we are going to see. For the stub matching, I'll open now one new Smith chart utility tool. Okay, so now I'll close the old one. Go back now here under the Smith chart utility tool, go to tools, open the Smith chart. Okay, I'll create a new one, new Smith chart. So now I'll design one stub matching for another different frequency and different impedances. So I can go for having one stub matching with, I'll let you know. Or for the same thing only we can do, let it be 2.4 only. I'll give my ZL as what I gave 10. What was the previous ZL I gave? 10 minus J10 or 10 minus J20 I'll give. Okay, and ZS star, if you see, I'll give it as 20, 20, and if it is a positive impedance, then I should give here negative minus J50. Okay, I'm giving another value. So where are my circuit points, impedance points are coming here. So now I want to design one matching with stub. So what are the stub elements corresponding here? You see, you have one M stub is there, then you have one open stub, one short stub is there. So I'll select one stub, that is my normal microstrip line stub. If you see that stub, if it is moving up in the, similar to the series inductor, it is moving up in the resistance circle. So where it is, it's following like this. I'll come till, now I'll stop here, okay, till somewhere here. Then I will take one open circuited stub that is coming here, but still I didn't reach exactly. This is, I should extend this point little more so that I can reach this point exactly. Still I little bit extend this, so I'm getting exactly. So can you make out, see, I am moving up in the resistance circle by one microstrip line, and then I am taking one open circuited stub that comes down in the conductance circle and came to this point. If you see, the response is very sharp, exactly at 2.4 gigahertz. But thing is, you are having a very narrow response. Okay, so this is the stub matching one design. I can even go with another kind of analysis also. So now how I'll find out these values is, so if you click on the first one, okay, if you click on the first one, it is having what is the value showing in the Smith chart window? It is 20.69 degrees. The next one is open stub. For that, it is showing what? It is showing here as 61.882 degrees. Okay. And what is the impedances you are having here? ZL value I have designed for 10 plus J20. And what is the ZS star I have done? It is for 20 minus j 50. Okay, so now it is now showing the values of the transmission line in terms of degrees. So now how can I convert this degrees to width and length? Suppose if I come back to my schematic window, I'll go to component palette. In that, you come to the transmission line microstrip. When you come to transmission line microstrip, you see here, scroll down, you can find one emblem. I'll take and put one emblem. Then what is the other one we used there? We used one open circuit. So ML open circuit is the microstrip line, which is open circuited line what I used. So these two are the components what I was using in my matched circuit design, isn't it? So you can go and check in your Smith chart. So one is normal microstrip line, other one is a open circuited microstrip line. So I'll come back to this window. Here, what are the things is there is, I have to use one, okay, I have to go for feeding the width and length for this transmission line, and what is the substrate definition. So for that, I'll go and take an M sub, I'll enter. It is asking which resolution you want. I will select millimeter wave resolution. You can even select mil or micron. Okay, I'll select millimeter wave. You come and click this. So now it is asking for the details of the substrate what I'm going to use. So what substrate I can go for using this is, I can have an RT duroid or FR4 substrate. So now I will be choosing one substrate specification here, that I will feed those values first, and then we'll come to the calculation of microstrip line values. So I will be taking the substrate thickness as H is a substrate thickness 0.8 mm. Then relative permittivity, I will not take it as 9.6, instead of that I will give 4.4. Then I can have the conductivity as 5. Okay, here instead of 1 I'll give it as 5, and it is 5.8, e to the power of 7. It is not 50, it is 7. Okay, then thickness of the conductor, okay, thickness of the conductor is 0 mm. There I will give T as 35 micrometer. It is micrometer, so you can type U, and loss tangent value it is given as 0. I'll give it as 0.02. Okay, so this is a substrate definition. First I have to finish it, then I will construct the circuit. So one microstrip line, then I will put the terminating resistor, go to simulation S parameter, take and put S parameter simulation, and take put term resistors on both the sides, then you connect it with the wires. Okay, so this is one connection. Here it is connecting. This is my open circuited line, and all should be grounded finally to the ground. This is not grounded here. Already it is an open circuit, so it should be left open. Okay, so what are the things I have here? One simulation controller. Okay, I have one simulation controller for S parameter simulation. So again, this one I will change it to start from 0.5 gigahertz, then you end it at 5 gigahertz because I am designing this for 2.4 gigahertz, and this one I will change it to 0.1 gigahertz. Okay, so this is my matching circuit, but still these values are default values. So how can we calculate this width and length is, I have to go back to tools. In that you have a line calculator tool. All of you see this, you have a line calculator tool. Give a start line calculator tool. So click on this, so window will come here. It is asking type of the microstrip line is mlen. You can open and see there are so many other lines are there. I will select mlen, then I'll be feeding the same values back here. What is the epsilon r I have selected? It's 4.4. And what is the conductive thickness, substrate thicknesses? It is 0.8 mm. It is 0.8. You change here as mm. And what is this one I have selected is 5.8. 5.8, and this is 7. And this is also meters. It should be in HU. No, it is not the conductor. It should be something. What was the previous default value? It was 35 micrometer. This should be 35 micrometer. 35. It should be 35 micrometer, and I think thickness should be 35. T should be 35 micrometer. Okay, I'll close this once again. No, you give. Go to tools back. Open the line calculator tool. Start the line calculator tool. Okay, so now I'll select this as 4.4 epsilon r, and then ur is nothing. Height of the substrate h is zero point 0.8. It's 0.8 mm. 0.8 mm. And HU you don't touch. Thickness of the substrate is, thickness of the conductor is, it is 35 micrometer. Go and change it as micrometer. And conductivity is 5.8. It's 5.8 e to the power of 7. And what else is there? Then tan delta is 0.02. Okay, the remaining all you leave it as such. This you should set properly. And this is a one more thing is which frequency you are designing, you are finding the length and width for the microstrip line is very important. Okay, so you have to give us 2.4. And now what is the thing we found out from that calculation is, we found out that what is the thing we found out? What is the dimension of this microstrip line? It was showing us 20.699 electrical length. This 20.699 is nothing but the electrical length of this microstrip line. So you go back to the transmission and calculator. Here you have to give the impedance as 50 ohm because we have standard impedance we have chosen as 50 ohm, and this one you give it as how much degrees it was there in this, it was showing as 20.699 degrees. So now you feed that 20.699 degrees. Okay, so you check all. First I have completed the substrate parameter. I gave the frequency is Z naught is 50 ohm, and E effective is nothing but the electrical length. That electrical length is retrieved from the length of the transmission line what it is showing in the Smith chart tool. So now I go back to the transmission and calculator, give as synthesize. Okay, when you give synthesize, okay, it will be doing the synthesizing. So now I'll change this unit to micrometer. I'll maintain this in micrometer. Once again I'll synthesize. Okay, so now you see what is the values it's showing. It's showing as 1502.47 micrometer, and L is showing as 3971.85 micrometer. Okay, then now what is the next calculation you have? Come back here. This one open circuited stub is there, no M log. For that, what was the degrees it was showing? You see in the Smith chart utility tool, it was showing as 61.88. Okay, so now I will minimize this window. Come back to this. Here you select whether it is M lock is appearing here. If M lock is not appearing means then you have to take it as again as mlin only. Let it be mlin only. Okay, let it be mlin only. Now the same thing I will maintain. Only thing is I'll change the degree here. It was what? 61.88. Okay, now I'll give again calculate. When I calculated this, you see what it is showing. It's showing as 1502 point. Width is showing as 1502 point. L is showing as 11873.9. Okay. So now I'll minimize this window. I'll save this if I want. I can give some name and save it. Minimize this window. Come back to the schematic tool. Here I will change this to, it was 1502.47 micrometer. Similarly, or I can keep it in millimeter because what is the thing we had, our resolution was this. I'll change it to millimeter so that at least you can have it even in millimeter also. Just do the synthesis once again. I think it's not changing. So we'll let it be in micrometer. Okay, now you come back to the schematic window. Here I will change it to as micrometer, and this one is how much. L was 3971.85. You have to note down all these values so that you can enter it later. Micrometer. Okay, and then here W is what? This W is the same thing because width will not change, only the length will change. With this again 1502.47 micrometer. Okay, and length I will change it as 11873.9 micrometer. Okay, so now I have changed the width and length. So any circuits involving microstrip line, you have to go to the tools. In that tools line calculator, you have to first feed the substrate definition, then you have to set the frequency and give the Z0 and E effective. E effective is nothing but the effective length of the transmission line. That will be getting converted to the physical length. Okay, so now I'll simulate this, save this design, then you simulate it. Okay, so now it is simulated. I'm opening. I'll go for plotting S11 first in dBs. Then I'll plot S22 in dBs. Okay, so where is my response? My response is not proper. Okay, then it means I have to do some tuning for that. So how can I do the tuning? As I already told you, you can go back to the schematic, select the tuning option. Okay, so one window will come. In that you can select the length, this length and this length and width of this also. Okay, then you open parallelly your graph, keep this in the corner here. You can change the step minimum maximum values if you want. I can have it in any value and I can just show the changes. So when you click, every time there will be a changes happening in this. This is nothing but the length. When I go, I am not getting much change, so I will try to change the length of this. Okay, both are width. I'll try to change the length. So now I'll just update the schematic and see how does my response is coming. So I'm not still getting exactly. Whereas 2.4 gigahertz I'm getting minus 9. So still I'll improve this. I'll just go for again tuning this. Once again I'll take the tuning component. Last two are width, and I think I have, okay, one is length and other one is width. Go back to the schematic, take this here. So this is one length. I'll try to change the length. Again here this is also the length. So let it be some 2. Okay, minimum value. This one also I will bring down. So still it is now see at 2.4 it has come down. So now I'll click this, update the schematic, close it. Okay, now if you check, put the marker here at 2.4, I'm getting somewhat better response. See here at 2.4, I'm getting minus 13. Similarly here also I'll place a marker at 2.4, I'm getting same minus 13. What about my S21? S21 at 2.4 I'm getting 2.4. It is minus little loss is there. It's minus 2, minus zero point 0.2. Okay, so these values are acceptable. So by using the tuning option, as soon as you update the schematic, you can go for completing the operation. It should be greater than minus 10 dB your responses. So this is a way how do we do our matching circuit design for stub as well as for the lumped pi type. Okay, so anything you have doubts, it will be clarified in the next session. Thank you.